Okay, let's unpack this. Usually when we talk about exams on here, it's all about um, memorizing a textbook.
Right, just regurgitate facts.
Exactly, regurgitate some definitions and, move on with your life. But today, we're looking at something different. This is the VMware VCF networking exam, specifically the VCAP, the 3V0-25.25. And honestly, looking at this source material, this feels less like a test. It feels more like a survival guide for a modern data center.
It really is. I mean, if you treat this just as a test, you're completely missing the point. This material, it effectively reverse engineers the entire nervous system of a software-defined data center. It forces you to understand how the plumbing actually works when you strip away all the marketing fluff.
And that's what we're going to do today. We're going to strip away the fluff.
Yeah.
We've got a stack of practice questions, architectural diagrams, all these technical specs here. And our mission is to figure out not just the right answer for the test, but why the architecture demands that specific answer.
Yeah.
Because some of these requirements, frankly, they seem a little counterintuitive at first.
They do. Until you realize that in a VCF environment, networking isn't just about cables anymore, it's code. And code has very, very specific rules.
Okay, so before we get into the heavy technical machinery, let's set the stage. Let's do the scouting report for this exam. If you are listening to this on the way to the testing center, don't panic, but this is a marathon.
It's a beast. 135 minutes.
That is over 2 hours of staring at network topologons. You're looking at what, 60 to 70 questions?
Yeah, somewhere in that range.
And the format is all over the place. Drag and drop, matching, multiple choice. But the thing that stuck out to me in the report was the passing score. It's 300.
The famous 300.
Now, to the uninitiated, 300 sounds incredibly low. Like, do I just need to spell my name right to pass?
It's a huge trap, isn't it?
It has to be.
It is. The scale starts at 100, so 300 is really the benchmark for competency. And in the VMware Advanced Professional world, competency doesn't mean you memorized a flashcard. It means if I drop you into a broken environment with a complex federation setup, you know which button restores connectivity and which button accidentally deletes the entire routing table.
Which is a perfect segue into our first major topic, the brains of the whole operation. The source material spends a lot of time on this idea of federation.
Right. Because the days of having one single data center in a basement somewhere are pretty much gone.
Exactly. So companies have a site in New York, a site in London, maybe a recovery site in Tokyo. So the question becomes, how do you manage that? If I need to update a firewall rule, do I really have to log into New York, make the change, then log into London, make the same change, and just hope I didn't make a typo?
Well, you could do that, but that's what we call a resume-generating event.
Because you're going to mess it up.
Inevitably. You'll forget one site, or you'll mistype an IP address, and suddenly London is dark. It's a governance nightmare. So the exam asks specifically about the component that solves this, and the answer is the global manager.
The global manager. It sounds impressive, but I want to push back on this a little bit. We're talking about adding another layer of management on top of the local managers that are already there. Isn't that just introducing a single point of failure? I mean, if the global manager goes down, do I lose my entire global network?
That's a common fear, but no. Think of it more like a franchise model. The global manager is corporate HQ. They set the menu, they decide the prices, and they push those policies down to all the local branches.
Okay.
If corporate HQ loses its internet connection, the local McDonald's doesn't stop flipping burgers. The local managers just keep running the existing configuration. You just can't push new global changes until it's back online.
Okay, that makes sense. So the global manager is the supreme authority for the centralized control, but the execution is all local.
Precisely. It synchronizes policies across all federated environments. You configure the rule once at the global level, and it ensures New York, London, and Tokyo are all perfectly aligned. It's about consistency, just as much as it is about efficiency.
All right, so we've got the brains sorted out. We know who's in charge. But what about the eyes? Because it's one thing to push a policy. It's a whole other thing to know if it's actually working. There's a question in the stack about troubleshooting visibility.
And visibility is, I think, the hardest part of virtual networking.
Right, because you can't just walk into the server room and trace a yellow cable to see where it's unplugged anymore. The cable is software.
And that software is running on physical hardware. So you have this complex layering. So when things break...
And they always break.
They always break, yeah. You need a tool that can see through both layers. The source material points directly to ARIA operations for networks.
Formerly Virtualized Network Insight, for the veterans listening. But why this specific tool? Why can't I just look at the NSX dashboard?
Because the NSX dashboard, it generally tells you what it thinks is happening in the virtual world. Area operations for networks is more like an X-ray machine. It gives you what they call underlay-overlay correlation.
Okay, unpack that for me. Underlay-overlay correlation.
Okay, so you have a VM that can't talk to a database. The virtual settings, they look fine, the firewall allows it, but the traffic just isn't moving. Area can trace that packet hop by hop and show you, hey, the virtual path is fine, but look here, physical switch number 4 in rack 2 is dropping packets because of a bad port.
Oh, wow. So it literally bridges the gap between the matrix and the real world.
Exactly. It provides that deep visibility across the entire path. Without it, the virtualization admin is blaming the network guy. The network guy is blaming the server guy.
And nobody fixes the problem.
Nobody fixes the problem.
Speaking of the bridge between the matrix and the real world, we need to talk about getting traffic out.
Yeah.
We've got all these VMs floating around in the software overlay, but eventually someone needs to check their email. They need to get to the physical internet.
The dreaded north-south traffic.
The source material highlights two critical components here. First, the gateway itself. The Tier 0 gateway.
The Tier 0 is your border control.
But why do we even need a Tier 0? I mean, we already have physical routers. Why create a virtual router just to talk to a physical router?
Flexibility. The Tier 0 gateway is the edge of your entire virtual kingdom. It allows you to terminate all your virtual networks, which might be overlapping or complex or changing every 5 minutes, and present a really clean, summarized interface to the physical world. It isolates the chaos of the virtual environment from the stability of the physical core.
Okay, so the Tier 0 is the diplomat. It stands at the border and talks to the hardware. But what language are they speaking? The source questions get really specific about protocols here.
And it's the standard language of the internet, BGP, Border Gateway Protocol.
I feel like BGP is the answer to every networking question eventually.
It usually is, but in VCF, it's doing something very, very specific. The Tier 0 gateway uses BGP to advertise reachability. It effectively shouts to the physical leaf switches, hey, I have these 50 new web servers over here. Send any traffic for them to me.
And the physical switch just listens.
If you configured the peering correctly, yes. And that's the beauty of it. It's dynamic. If you spin up a new network segment in the software, the Tier 0 automatically updates the physical router via BGP. You don't have to call the network team at 3 a.m. and ask them to type in a static route.
That is the dream.
Yeah.
No 3 a.m. phone calls, but, and there's always a but, this handoff between virtual and physical relies on the plumbing actually working.
Yeah.
And this is where we get into my favorite part of the source material, the gotcha question.
Ah, the MTU question.
Maximum transmission unit. Basically, how big can a packet be before it gets stuck in the pipe? Now, for the last 30 years, the standard Ethernet MPU has been 1,500 bytes. It's written in stone. It's the law. But the source material says, if you set your physical network to 1,500 bytes in a VCF environment, you are going to fail. The minimum recommended MTU is 1,600 bytes, or really as high as jumbo frames allow. But why? Why does VCF need to break this standard?
It's not breaking the standard so much as it is abusing it. Remember, we are doing overlay networking. We take the original packet from the VM and we encapsulate it to send it across the wire.
We wrap it in an envelope.
Yes. And specifically, VCF uses the Genv protocol for that envelope. Now, that Genv header, it contains metadata. It takes up space. We're talking about 50 to 100 bytes usually.
I can see where this is going.
If your inner packet is already at the full size 1,500 bytes and you add a 50-byte Genv header, your total packet size is now 1,550 bytes.
And if the physical wire is stripped at 1,500?
So it drops it. The physical switch just looks at it and says, you're too fat, you can't come in.
But here's the insidious part. Small packets, like a ping command, they would still work, right?
Yeah.
Because a tiny ping plus the header is still way under 1,500.
Yeah. That is exactly why this is a nightmare to troubleshoot. You can ping the server, so you think connectivity is fine. But the moment the application tries to send a large file or a complex database query, the packet hits that 1,500 limit and just vanishes into the void.
A silent killer. So the takeaway for the exam and for real life is that the physical plumbing must be wider than the virtual traffic. Minimum 1,600 bytes on the physical switches to accommodate that Genv overhead.
It's completely non-negotiable.
All right, let's pivot from plumbing to security. In the old days, if I wanted to secure a server, I bought a firewall appliance, a big metal box. I'd plug it in, and I would force all my traffic to go through it.
The perimeter model. Great for that north-south traffic, but terrible for everything else.
Right, and the source material focuses heavily on the distributed firewall, or DFW. The question asks, where are the policies actually enforced? And the answer is the hypervisor kernel.
Which is a profound shift in architecture.
But play devil's advocate here. Isn't putting the firewall in the kernel dangerous or slow? I mean, you're using the server's CPU to do packet inspection.
It's actually the complete opposite. Think about the alternative.
Yeah.
If I have two VMs on the same server and I want to firewall the traffic between them using a physical appliance, I have to send the traffic out of the server, across the network, to the firewall, have it inspected, and then send it back to the very same server.
That's the hairpin effect.
It's incredibly inefficient. It just floods your network with unnecessary traffic. By putting the firewall in the hypervisor kernel, right at the VNIC, the virtual network card, we inspect the traffic before it even hits the wire. It's what we call microsegmentation.
So every single VM has its own personal bodyguard.
Exactly. And because it's distributed, the throughput scales with the cluster. You don't have a single choke point. It's infinitely more scalable than a hardware appliance for that east-west traffic.
Okay, so we've built a secure network. We've verified the MTU. We've got BGP talking. But now we need to talk about uptime, because none of this matters if the application crashes.
Availability is king.
The source brings up the NSX load balancer. And sure, we all know what a load balancer does. It spreads traffic around. But there's a nuance here regarding stretched clusters.
This is the disaster recovery scenario.
Right. You have Site A and Site B. You want them to act as one giant supercluster. So if a meteor hits Site A, the VMs just keep running on Site B.
It's the gold standard for availability, but it comes with a very strict price tag in terms of physics.
The source material asks for the maximum round trip time, or RTT, latency allowed between these sites. And the number is 5 milliseconds.
5 milliseconds.
That is incredibly fast. I mean, a blink of an eye is, what, 100 milliseconds?
Yeah.
Why is the tolerance so low? If I have 6 meters latency, does the system really just fail?
It's not that the network fails, it's that the storage fails. Stretched clusters rely on synchronous storage writes.
Walk me through that.
Okay. A VM at Site A wants to write a file to disk. Because it's a stretched cluster, the storage system has to write that data to the drive at Site A and send it to Site B, write it there, and wait for Site B to send back a receipt saying, got it. Only then does it tell the VM, okay, your write is complete.
So the VM is just frozen, waiting for that receipt to come back.
Exactly. It's like two musicians trying to play a duet over Zoom. If the lag is too high, they can't stay in rhythm. If that round trip takes longer than 5 meters, the wait time for every single disk operation becomes noticeable. The application starts to crawl, databases time out, and eventually the whole cluster becomes unstable.
So 5 meters isn't just a suggestion. It's the speed limit of physics for synchronous storage.
You can virtualize a lot of things, but you cannot virtualize the speed of light.
That is a bumper sticker waiting to happen. You cannot virtualize the speed of light. Okay, we're coming down to the final section. Deployment and dependencies. The order of operations.
This is where a lot of people fail the exam, and frankly, the deployment in real life.
The source defines something called a host transport node. Simple definition first. What is it?
It's the workhorse. It's simply an ESXi host, the physical server that has been installed with the NSX agents. It's joined the transport zone. It's ready to pass those GNF packets.
Okay, simple enough. But then we have this acronym, AVN, Application Virtual Network.
This is a huge part of the VCF standardized architecture.
The question asks, what must be present before you can deploy an AVN? You can't just click go.
No. The prerequisite is that you must have an edge cluster available in the management domain.
Why? Why can't I just deploy the network and worry about the edge later?
Think about what AVNs are used for. In VCF, these networks usually host management components, things like that area suite we talked about earlier. These tools need to send alerts, which is email, authenticate users, which is LDAP, or download updates from the internet.
They need to talk to the outside world.
Exactly. And who provides the path to the outside world? The edge cluster. It hosts the Tier 0 and Tier 1 gateways. If you try to deploy an AVN without an edge cluster, it's like trying to build a penthouse on a building that has no elevator and no stairs. You can build the room, but nobody can get in or out.
It's a dependency chain. You need the edge to provide the routing services that the AVN consumes.
Correct. And the exam loves to test these dependencies because in the real world, if you do this out of order, the automated deployment engine just fails. It doesn't ask you nicely to try again. It just errors out.
And nobody wants to be debugging a failed deployment log file.
No, nobody.
I hope this deep dive gave you the context you need to tackled those 60 to 70 questions.
Or at least gave you enough ammo to argue with your storage admin about latency.
That is always a worthy cause. Go crush that exam, check your MTU settings, and we will see you on the next deep dive.